必须的。
This brings us to the end of the 7th module of the Google Cloud Computing Foundations course. This brings us to the end of the 7th module of the Google Cloud Computing Foundations course. Let's do a quick summary. You started by exploring virtual private clouds. A virtual private cloud, or VPC, is a secure, individual, private cloud computing model hosted within a public cloud, like Google Cloud. A virtual private cloud is made up of subnetworks or subnets, and each subnet must be configured with a private IP CIDR address. You examined Google's network architecture, including regions and points of presence. You also learned about 5 Google Cloud networking products: Virtual Private Cloud, Cloud Load Balancing, Cloud CDN, Cloud Interconnect, and Cloud DNS. You learned how to use multiple VPC networks with VPC network peering and shared VPC. You explored options to build hybrid clouds. Options include IPsec VPN protocol, direct peering, carrier peering, dedicated interconnect, and partner interconnect. And finally, you examined load balancing options, including cloud load balancing.
Welcome to Module 8 of the Google Cloud Computing. Welcome to Module 8 of the Google Cloud Computing Foundations course, Keeping an Eye on Things. In this section of the course, you'll look at the role that Google Cloud can play in automating the creation and management of your Google Cloud resources and ensuring that your infrastructure and applications run optimally. This means that you'll learn about infrastructure as code, IAC, explore Terraform as an IAC option, examine the role of monitoring, logging, error reporting, tracing, and profiling in the cloud, and learn how to use Google Cloud Observability for monitoring, logging, error reporting, tracing, and profiling. The module agenda follows the objectives. You'll begin with an introduction to infrastructure as code before you move on to Terraform as an IAC tool. You'll then learn about the importance of monitoring and managing existing services, applications, and infrastructure. Next, you'll look at the integrated tools that comprise Google Cloud Observability. From there, you'll learn how to use cloud monitoring through a hands-on lab. And finally, the module concludes with a short quiz and a recap of the topics covered. Let's start with the first topic, where we'll discuss the concept of infrastructure as code. Creating an environment in Google Cloud can mean lots of work, like setting up a compute network and storage resources, and then monitoring their configurations. This process can be done manually by writing the commands you need to set up your environment the way you want. However, this is labor-intensive. If you want to change the environment, it requires updating commands. Or if you want to clone an environment, you must manually write new commands. As the name implies, infrastructure as code, or IAC, is taking what a required infrastructure needs to look like and defining it as code. You capture the code in a template file that's both human-readable and machine-consumable. IAC tools allow for the creation of entire architectures by using templates. The template is a configuration file that supplies the details of the infrastructure. Rather than having to use a console or run commands manually to build all parts of the system, the template is used to automatically build the infrastructure. The same template enables resources to be automatically updated and/or deleted as required. Because templates are treated as code, they can be stored in repositories, tracked using version control systems, and shared with other users. Templates can also be used for disaster recovery. If for any reason the infrastructure must be rebuilt, the templates can be used to automatically recover.
Now let's explore Terraform. Now let's explore Terraform, an open source infrastructure as code tool. You saw in the last section how manually creating an environment in Google Cloud can be a labor-intensive task, and how using a template can make the process more efficient. Terraform is an open-source tool that lets you use templates to provision Google Cloud resources. To use Terraform, you create a template file by using HashiCorp configuration language HCL, which describes what the components of the environment should look like. Terraform then uses that template to determine the actions needed to create the environment your template describes. If you need to change the environment, you can edit your template and then use Terraform to update the environment to match the change. A deployment can be repeated as many times as required with consistent results, and you can delete an entire deployment with one command or click. Terraform uses the underlying APIs of each Google Cloud service to deploy your resources. This enables you to deploy almost everything we have seen so far, from instances, instance templates and groups, to VPC networks, firewall rules, VPN tunnels, cloud routers, and load balancers. You can store and version control your Terraform templates in industry-standard Git repositories, such as GitHub, GitLab, or Bitbucket, and integrate them with Infrastructure Manager for automated deployments. In addition to Terraform, Google Cloud also provides support for other third-party open-source IAC tools.
In this section, you'll learn which activities need to be performed to monitor. In this section, you'll learn which activities need to be performed to monitor and manage existing services, applications, and infrastructure. Monitoring is the foundation of product reliability. It reveals what needs urgent attention and shows trends in application usage patterns, which can yield better capacity planning and generally help improve an application client's experience and minimize pain points. In Google's Site Reliability Engineering book, which is available at landing.google.com/sre/books, monitoring is defined as collecting, processing, aggregating, and displaying real-time quantitative data about a system, such as query counts and types, error counts and types, processing times, and server lifetimes. With monitoring, you can ensure continued system operations, uncover trend analyses over time, build dashboards, alert personnel when systems violate predefined service level objectives, SLOs, compare systems and any changes to them, and provide data for improved incident response, just to name a few tasks. An application client normally only sees the public side of a product, and as a result, developers and business stakeholders both tend to think that the most important way to make the client happy is by spending the most time and effort on developing that part of the product. However, to be truly reliable, even the best products must be deployed into environments with enough capacity to handle the anticipated client load. Great products also need thorough testing, preferably automated, and a refined continuous integration, continuous development, CI/CD, release pipeline. Blameless postmortems and root cause analyses are the DevOps team's way of letting the client know why an incident happened and why it's unlikely to happen again. In this context, we're discussing a system or software failure, but the term incident can also be used to describe a breach of security. Transparency here is crucial to building trust.
Now, let's explore Google Cloud. Now, let's explore Google Cloud Observability. Google Cloud Observability provides powerful monitoring, logging, error reporting, and debugging for applications in the cloud. It equips you with insight into the health, performance, and availability of cloud-powered apps, enabling you to find and fix issues faster. When DevOps personnel want to track exactly what's happening inside Google Cloud projects, they often first think of monitoring. As stated previously, monitoring starts with signal data. Metrics take measurements and use math to align those measurements over time. For example, it might be taking raw CPU usage measurement values and averaging them to produce a single value per minute. Google Cloud, by default, collects more than 1,000 different streams of metric data, which can be incorporated into dashboards, alerts, and several other key tools. When data scientists run massive, scalable queries in BigQuery, it's important for them to know how many queries are currently in flight, how many bytes have been scanned and added to the bill, and data slot usage patterns. It could also be critical to DevOps teams that run containerized applications in Cloud Run to know CPU and memory utilization and app build time. And if those same DevOps teams want to enhance the signal metrics from their custom application wherever it's running, they could use the open-source observability framework for cloud-native software, OpenTelemetry, and create their own metrics. Workloads on Compute Engine will benefit from CPU and memory utilization data, along with uptime, disk throughput, and many other metrics. Cloud monitoring provides visibility into the performance, uptime, and overall health of cloud-powered applications. It collects metrics, events, and metadata from projects, logs, services, systems, agents, custom code, and various common application components, including Cassandra, Nginx, Apache Web Server, and Elasticsearch. Monitoring ingests that data and generates insights through dashboards, metrics explorer charts, and automated alerts. Most log analysis starts with Google Cloud's integrated Logs Explorer. Logging entries can also be exported to several destinations for alternative or further analysis. Pub/Sub messages can be analyzed in near real time by using custom code or stream processing technologies like Dataflow. BigQuery allows analysts to examine logging data through SQL queries, and archived log files in cloud storage can be analyzed with several tools and techniques. Log data can be exported as files to cloud storage, as messages through Pub/Sub, or into BigQuery tables. Logs-based metrics can be created and integrated into cloud monitoring dashboards, alerts, and service SLOs. Default log retention in cloud logging depends on the log type. Data access logs are retained by default for 30 days, but this is configurable for 3,650 days. Admin logs are stored by default for 400 days. Export logs to cloud storage or BigQuery to extend retention. The Google Cloud logs that are visible to you in cloud logging vary depending on which Google Cloud resources you use in your Google Cloud project or organization. 4 main log categories are audit logs, agent logs, network logs, and service logs. Cloud audit logs helps answer the question who did what, where, and when. Admin activity tracks configuration changes. Data access tracks calls that read the configuration or metadata of resources and user-driven calls that create, modify, or read user-provided resource data. System events are non-human Google Cloud administrative actions that change the configuration of resources. Access transparency provides you with logs that capture the actions Google personnel take when they access your content. Agent logs use a Google customized and packaged Ops agent that can be installed on any AWS or Google Cloud VM to ingest log data from Google Cloud instances, for example, Compute Engine, managed VMs or containers, and AWS EC2 instances. Network logs provide both network and security operations with in-depth network service telemetry. VPC flow logs record samples of VPC network flow and can be used for network monitoring, forensics, real-time security analysis, and expense optimization. Firewall rules logging lets you audit, verify, and analyze the effects of your firewall rules. NAT gateway logs capture information on NAT network connections and errors. Service logs provide access to logs created by developers who deploy code to Google Cloud. For example, if they use Node.js to build a container and deploy it to Cloud Run, any logging to standard out or standard error will automatically be sent to Cloud Logging for easy, centralized viewing. Error reporting counts, analyzes, and aggregates the crashes in your running cloud services. Crashes in most modern languages are exceptions, which are not caught and handled by the code itself. Its management interface displays the results with sorting and filtering capabilities. A dedicated view shows the error details, time chart, occurrences, affected user count, first and last seen dates, and a cleaned exception stack trace. You can also create alerts to receive notifications on new errors. CloudTrace, based on the tools Google uses on its production services, is a tracing system that collects latency data from your distributed applications and displays it in the Google Cloud Console. Trace can capture traces from applications deployed on App Engine, Compute Engine VMs, and Google Kubernetes Engine containers. Performance insights are provided in near real time, and Trace automatically analyzes all of your application's traces to generate in-depth latency reports to surface performance degradations. Trace continuously gathers and analyzes trace data to automatically identify recent changes to your application's performance. Poorly performing code increases the latency and cost of applications and web services every day, but nobody knows or does anything about it. Cloud Profiler changes this by using statistical techniques and extremely low-impact instrumentation that runs across all production application instances to provide a complete CPU and heap picture of an application without slowing it down. With broad platform support that includes Compute Engine VMs, App Engine, and Kubernetes, Profiler lets developers analyze applications that run anywhere, including Google Cloud, other cloud platforms, or on-premises, with support for Java, Go, Python, and Node.js. Profiler presents the call hierarchy and resource consumption of the relevant function in an interactive flame graph that helps developers understand which paths consume the most resources and the different ways in which their code is actually called.
Let's learn about cloud monitoring with this hands-on lab. Let's learn about cloud monitoring with this hands-on lab. In the lab titled Cloud Monitoring Quick Start, you'll monitor a Compute Engine virtual machine instance with cloud monitoring. During this lab, you'll create a Compute Engine instance, add an Apache 2 HTTP server to the instance, create an uptime check and alerting policy, create a dashboard and chart, view logs, and check the uptime check results and triggered alerts.
뭐요? Emang lu pikir kayak gini nggak capek apa? Berapa teks kira? Udah coba berjam-jam mau nyoba pakai AI. Uh, udah 1 jam lagi, Cok. Ya kan? Udah 1 jam lagi, gila gak kerasa anjing. Udah 1 jam lagi, Cok.
This brings us to the end of the 8th module of the Google Cloud Computing. This brings us to This brings us to the end of the 8th module of the Google Cloud Computing Foundations course. Let's do a quick summary. First, you learnt about infrastructure as code, IAC. Then you explored Terraform as an IAC option. Next, you examined the role of monitoring, logging, error reporting, tracing, and profiling in the cloud. And finally, you learned how to use Google Cloud Observability for monitoring, logging, error reporting, tracing, and profiling.
Welcome to Module 9 of Welcome to Module 9 of the Google Cloud Computing Foundations course. You have the data, but what are you doing with it? In this module, you'll look at some managed services that Google offers to process your big data. This means that you'll explore big data managed services in the cloud, examine using Dataproc to run Apache Hadoop, Apache Spark, and other big data technologies as a managed service in the cloud, learn about building ETL pipelines as a managed service using Dataflow, and explore BigQuery as a managed data warehouse and analytics engine. The module agenda follows the objectives, starting with an introduction to big data managed services in the cloud, before moving on to how big data operations can be used through Dataproc. You'll then complete 2 labs by using the Google Cloud Console and the G-Cloud CLI to create a Dataproc cluster and perform various tasks. After the labs, you'll explore the use of Dataflow to perform extract, transform, and load operations. The following 2 labs provide an opportunity to learn more about Dataflow. In the first one, you'll use a Dataflow template to create a streaming pipeline. In the second, you'll set up a Python development environment, get the Dataflow SDK for Python, and use the Google Cloud Console to run an example pipeline. In the final section, you'll learn about the role of BigQuery as a data warehouse before it finishes with another hands-on lab to learn about data prep. The module concludes with a final hands-on lab, followed by a short quiz and a recap of the topics covered. Let's get started.
Gitu, Bro. Nggak gitu, Bro. Gitu.
In this first section, we'll discuss big data managed services in the cloud. Before we explore this in detail, let's take a moment to conceptualize big data. Enterprise storage systems are leaving the terabyte behind as a measure of data size, with petabytes becoming the norm. We know that 1 petabyte is 1 million gigabytes, or 1,000 terabytes. But how big is that? From one perspective, a petabyte of data might seem like more than you'll ever need. For example, you need a stack of floppy disks higher than 12 Empire State Buildings to store 1 petabyte. If you wanted to download 1 petabyte over a 4G network, you'd have to sit and wait for 27 years. You'd also need 1 petabyte of storage for every tweet ever tweeted, multiplied by 50. So 1 petabyte is pretty big. If we look at it from a different perspective, though, 1 petabyte is only enough to store 2 micrograms of DNA, or 1 day's worth of video uploaded to YouTube. So for some industries, a petabyte of data might not be much at all. Every company stores data in some way, and now they're trying to use that data to gain some insight into their business operations. This is where big data comes in. Big data architectures allow companies to analyze their stored data to learn about their business. In this module, we'll focus on 3 managed services that Google offers for the processing of data. For companies that have already invested in Apache Hadoop and Apache Spark and want to continue using these tools, Dataproc provides a great way to run open source software in Google Cloud. However, companies looking for a streaming data solution might be more interested in Dataflow as a managed service. Dataflow is optimized for large-scale batch processing or long-running streaming processing of structured and unstructured data. The third managed service that we'll look at is BigQuery, which provides a data analytics solution optimized for getting answers rapidly over petabyte-scale datasets. BigQuery allows for fast SQL unstructured data. In this section, you'll learn how Dataproc
Lab lahat. Anjing lab day, cuy. Ayo.
In this section, you'll learn how Dataproc provides a fast, easy, cost-effective way to run Apache Hadoop and Apache Spark. Apache Hadoop and Apache Spark are open source technologies that often are the foundation of big data processing. Apache Hadoop is a set of tools and technologies which enables a cluster of computers to store and process large volumes of data. It intelligently ties individual computers together in a cluster to distribute the storage and processing of data. Apache Spark is a unified analytics engine for large-scale data processing and achieves high performance for both batch and stream data. Dataproc is a managed Spark and Hadoop service that lets you use open-source data tools for batch processing, querying, streaming, and machine learning. Dataproc automation helps you create clusters quickly, manage them easily, and because clusters are typically run ephemerally, you save money as they are turned off when you don't need them. Let's look at the key features of Dataproc. Cost-effective. Dataproc is priced at 1 cent per virtual CPU per cluster per hour, on top of any other Google Cloud resources you use. In addition, Dataproc clusters can include preemptible instances that have lower compute prices. You use and pay for things only when you need them. Fast and scalable. Dataproc clusters are quick to start, scale, and shut down, and each of these operations takes 90 seconds or less on average.
Ayan aja itu.
Clusters can be created and scaled quickly with many virtual machine types, disk sizes, number of nodes, and networking options. Open source ecosystem.
Mama cuy.
You can use Spark and Hadoop tools, libraries, and documentation with Dataproc. Dataproc provides frequent updates to native versions of Spark, Hadoop, Pig, and Hive, so learning new tools or APIs is not necessary, and you can move existing projects or ETL pipelines without redevelopment. Fully managed. You can easily interact with clusters in Spark or Hadoop jobs without the assistance of an administrator or special software, through the Google Cloud Console, the Google Cloud SDK, or the Dataproc REST API. When you're done with a cluster, simply turn it off, so money isn't spent on an idle cluster. Image versioning. Dataproc's image versioning feature lets you switch between different versions of Apache Spark, Apache Hadoop, and other tools. Built-in integration. The built-in integration with cloud storage, BigQuery, and Bigtable ensures that data will not be lost. This, together with cloud logging and cloud monitoring, provides a complete data platform and not just a Spark or Hadoop cluster. For example, you can use Dataproc to effortlessly extract, transform, and load terabytes of raw log data directly into BigQuery for business reporting. Let's look at a few Dataproc use cases. In this first example, a customer processes 50 gigabytes of text log data per day from several sources. The objective is to produce aggregated data that is then loaded into databases from which metrics are gathered for daily reporting, management dashboards, and analysis. Until now, they have used a dedicated on-premises cluster to store and process the logs with MapReduce. So what's the solution? First, cloud storage can act as a landing zone for the log data at a low cost. A Dataproc cluster can then be created in less than 2 minutes to process this data with their existing MapReduce. Once completed, the Dataproc cluster can be removed immediately. In terms of value, instead of running all the time and incurring costs even when not used, Dataproc only runs to process the logs, which reduces cost and complexity. Now let's analyze a second example. In this organization, analysts rely on and are comfortable using Spark Shell. However, their IT department is concerned about the increase in usage and how to scale their cluster, which is running in standalone mode. The solution is for Dataproc to create clusters that scale for speed and mitigate any single point of failure. Since Dataproc supports Spark, Spark SQL, and PySpark, they could use the web interface, Cloud SDK, or the native Spark shell through SSH. The value is Dataproc's ability to quickly unlock the power of the cloud for anyone without added technical complexity. Running complex computations would take seconds instead of minutes or hours. In this third example, a customer uses the Spark machine learning libraries, MLlib, to run classification algorithms on very large datasets. They rely on cloud-based machines where they install and customize Spark. Because Spark and the MLlib can be installed on any Dataproc cluster, the customer can save time by quickly creating Dataproc clusters. Any additional customizations can be applied easily to the entire cluster through initialization actions. To monitor workflows, they can use the built-in cloud logging and cloud monitoring. In terms of value, resources can be focused on the data with Dataproc, not spent on cluster creation and management. Integrations with new Google Cloud products also unlock new features for Spark clusters. This is the first of 2 labs where we'll work with Dataproc. In this lab, we'll use
Ya gue ya.
This is the first of 2 labs where we'll work with Dataproc. In this lab, we'll use the Google Cloud Console. We'll create a Dataproc cluster, run a simple Apache Spark job in the cluster, and modify the number of workers in the cluster by using the Google Cloud Console. During this lab, you'll create a cluster, submit a job, and then view the job output.
70 konon cuma 4% tadi gitu anjing. Oh, intinya gitu dibilang capeknya itu yang itu oh tidak kami tidak tertarik serius sudahnya gue Anjing. Beraya begini. Capek semuanya. Oh, isi. Gua kan udah ngirim tuh ya. Gua kan udah ngirim kok. Ini pada gak nyampe-nyampe sih gitu. Kok gak ada sih gitu. Gue sih nggak tahu ya apa gitu. Itu kan membantu juga gitu. Guys, itu cuma 4% anjing tadi tuh. Cuma 4% naik dari 57 ke 57 kayak gitu. Target gitu. Nah, iya. Lama anjing di nyata coba kayak gini tuh. Oh, ini goblok. gini nih kalau gue masih sempat ke channel kali, gue bisa tepat waktu gitu. Gue nggak nyari sekarang gitu. Kayaknya ada. Jadi misalkan, ay ginagawa cok, ano ko siya idea. Sih iya. Ya Allah, ya Robi. Iya, beres. Sini muridnya. Nama Icing kan, gue nggak jawab guys gitu. Main aing maksa di pan tegena muridnya. Ya murid ada mana? Ada misalnya. Ya. Astagfirullah. Jangan tadi saya nawan wae. Astagfirullah. Gue sih kok gitu kan. Bagian dan bagian. Video video. Kok merah sih? Nah, tinggal cerita.
This next lab is similar to the previous one.
Jadi dewa ini.
This next lab is similar to the previous one, except this time we'll use the G-Cloud CLI for Google Cloud. We'll create another Dataproc cluster and run another simple Apache Spark job in the cluster. This time, though, we'll modify the number of workers in the cluster by using the G-Cloud CLI. During this lab, you'll create a cluster, submit a job, and update a cluster.
Cok, hampir. Aduh, aing kumanya aing senang dan kutip karunya teh sia kuliah rek. Cok. Aing kata sia. Aing ya. Aing dewek gitu. Suntik. Paham itu. Satu. Aduh, dia gitu tanya seperti itu ada sih kayak gitu kan ya aduh semua itu di gitu jadi kamu jalan ya ini kita buat jangan sampai bukan gitu kurang ajar gitu gitu kurang ajar gitu. Oh, si region wah nggak ada region anjing. Era pating di badan kawan orang tahu ya kawan tuh biasa oh mention no biasa oh ini biasa semua lagi rumuskan gitu semua asli ini lại là itu mungkin kelihatan gitu aduh Gini cowok, pertama gini cowok, gitu. Hobi gitu pertama. Pertama, kedua adalah gitu. Di, pasti saya masalah sih gitu. Nggak bisa dia masuk bercanda itu ini. Bercanda emang. Tapi gimana, maksudnya gimana? Masih bocah gitu ya, gitu. Mungkin kalau banding belum itu wah itu ya maksudnya bercanda jadi gini tapi nonton berapa kali udah saya kayak itu bosan gitu kunaon karena kia itu kudu mayar gitu iya wah ayah iya apa gitu itu lupa gitu nah ayah bayar jadi ayah itu saya itu mulai mau lanjut nang 10.000 hanya menyukai yang main lagi gitu serius ya sampai jadi video berapa itu 5 bulan buku kan bisa kenapa gitu gitu jangan ada di kan ada ya ini ibaratnya gitu ibaratnya studi ya bahwa ada ini segitu dong jadi kita gitu gitu karena bosan untuk saya ya gitu bayar gitu ini ngeri ya itu banyak nyambung banyak aktor gitu tuh gitu masuk kan anh được mình phải mua kan đây mình còn gì cứ phải chạy như thế nếu mà có thể anh những việc bất biệt mình ép ta chọn trong mình đúng rồi nhà của mi nhà gọi ngon ví dụ mana itu itu aja kesini buat aing les sebenarnya kita kan les gitu maksudnya kan ada gitu hanya minder wah serius aja hanya minder wah serius minder gitu sama betul anh sống này nè ôi shit nó phải như vậy vô công ơi mới vậy vậy kia nhé và tôi tôi cái gì vậy sao đấy tôi vào rồi chơi wish it's it bisa sih ada di sana gitu tapi mainnya bisa berjalan gitu kan makanya awal ini jadi ada game gitu aja game kemarin sama dan minder gitu, mungkin minder, mungkin gitu. Itu yang kawan aku gitu. Karena saya coba aing di tempat kelas itu aing, ya aing di tempat kelas aing asalnya ya, aing gitu. Aing kemudian sebenarnya cari ilham bukan jadi ada yang saling lagi gitu. Skill gitu. Jangan beda sih. Jadi sakit. Itu bisa sih dia. Ayo jangan kasih dikit. Ayo jangan kasih dikit. Ulit minum air gitu ikut bisa gitu. Sisi itu air di si mandi begitu. Cium gitu nyata. Ini yang kalau lebih kan siap sekali lebih beda gitu. Iya, eh, wow sih ya. Kayak gitu deh gini. Kayak saya aing lagi. Aing turun aing ki. Suku aing gitu jadi kita kan ya ke aing gitu ke dia. Eh. Sebut masih tuh. Oh, ini bukan tuh. Aing kebayang kene sih. Seberang. Transisi. Di sini. Seberang. Gitu. Jangan. Aing ternyata tuh. Aing kira cuma ingat atuh ingat. Ingat tuh. Kan kan nyebutnya ini teh. Wah, gitu sih. Misi ya. Halus gitu. Oh, gitu. Wah, gitu. Siapa? Hanya kasih.
Now let's explore how you can use
Nah, karena aing teh tapi kan kultur kan mau bisa dibawa mau bisa apa ya bawa tuh aing dari apa ke gitu ibaratnya gitu.
Now let's explore how you can use data flow to perform extract, transform, and load operations. With Dataproc, you can migrate your original big data deployment with Apache Hadoop and Apache Spark to a fully managed service provided by Google Cloud. But how do you process both batch and streaming data if it's not Hadoop dependent? This is where Dataflow comes in. Dataflow is a managed service offered by Google that's optimized for large-scale batch processing or long-running stream processing. Dataflow creates a pipeline to process both streaming data and batch data. Process, in this case, refers to the steps to extract, transform, and load data, or ETL. When building a data pipeline, data engineers often encounter challenges related to coding the pipeline design and implementing and serving the pipeline at scale. During the pipeline design phase, you should consider a few questions. Will the pipeline code be compatible with both batch and streaming data, or will it need to be refactored? Will the pipeline code software development kit, or SDK, that's being used have all the transformations, mid-flight aggregations, and windowing? Will it be able to handle late data? And are there existing templates or solutions that should be referenced? Dataflow fully automates operational tasks like resource management and performance optimization. All resources are provided on demand and scale to meet requirements. Dataflow provides built-in support for fault-tolerant execution that's consistent and correct regardless of data size, cluster size, processing pattern, or pipeline complexity. Through its integration with the Google Cloud Console, Dataflow provides statistics such as pipeline throughput, lag, and consolidated worker log inspection in near real time. It also integrates with cloud storage, PubSub, Data Store, Bigtable, and BigQuery for seamless data processing between platforms. Now let's work through a Dataflow lab that uses templates. You'll use the PubSub to BigQuery template that Google provides to create a streaming pipeline in Dataflow. Note that you'll have the option to use the Cloud Shell command line or the Google Cloud Console. If you want experience using both methods, run through this lab a second time. So during this lab, you'll learn how to create a BigQuery dataset and table by using Cloud Shell and or the Google Cloud Console, run the pipeline, and submit a query.
Ngobrol gitu doang. Shit, itu gitu. Pas. Jangan pas dikatakan ke Bu Elin gitu ya. Bu Elin keren gitu. Aing kan aing tanyakan nanti saya oh dia dulu ya gitu aing. Kan yang lain mah. Aing mah hal-hal dikit mah. Simple oh ya dia. Tapi itu lu pasti ternyata KB gitu. Pasti bohong aja pokoknya. Wait, shit, you hold on. Shit, jadi ini kan itu. Aing banget. Bu Elin jadi aing ini jadi pun aing gitu. Aing gitu. Ini sebenarnya Ting kawan lagi skill sebenarnya bahkan sakit gitu ya sakit tapi sangat sakit memang jarang gitu guys terus tidak saja nulis bisa soalnya buat misal misalkan di contoh ya contoh ya yang siapa di Indonesia karena itu hidayah yang bisa mencari teman daya jadi sejarah sejarah sang kelas saya pernah ada kecil ini banyak gitu ini kadoknya gitu manggil daya begitu panggilan tapi SMA yang dimanggil lagi ini masih manggil gitu malamnya manggil lagi kita nah gitu bisa sama aja sebenarnya itu baik itu enggak segitu itu itu modal dari kan si ibu pas dulu itu ya coba tidak siapa skill jadi skill ya maksudnya di air dan tentunya intas harus belum tentu yang sebagus mainan gitu karena kamu misalkan baca itu bisa untuk kau ke air gitu dan kalau itu gitu awalnya sih itu siang si si skill si lebih tadinya gitu di luar sana rasa udah bisa siang pasang udah naik dari kecil banget gitu tingginya tarik nafas tarik mana nih gitu kan itu apa di HP itu lebih kayak gitu bagus itu banyak kan bagus bagus gitu cuman minta cuma sih yang belajar gitu Serapi ya ini misalnya ada yang isi kalau panjang ini kayak ini kan Serapi jual ada kan kan bisa dibeli sudah pernah ibu cuci sebelah sekian ya mana jual Serapi kan ah Serapi gitu tidak bisa ngobrol dengan ibu tidak buat tiga pas dua gitu pas dua kasih dulu tiga gitu Anh tiba dulu awal. Ya, từ cái chỗ anh cho mình cho hai cho tự cái à, của mấy cái tapi lain anh perlu kasih sikap tema itu apa gitu. Jadi konteksnya gitu. Iya. Sekolah umum gitu. Jadi privat. Baru masih gitu. Nah, tapi aing pakai SMA. Iya, aing apa sih apa ini aing maksudnya aing menjadikan SMA negeri satu itu sebagai cadangan gitu, semua aing sebagai cadangan. Parah sih coba aing. Iya, ayo aing main tambah.
In this next lab, we'll use the data flow
kita terima gitu. Ini kan kikil
In this next lab, we'll use the Dataflow SDK for Python to run an example pipeline. You'll learn how to set up a Python development environment, get the Dataflow SDK for Python, and run an example pipeline by using the Google Cloud Console.
lab để gì thế? Hostel. Itu nyawa sebut Hakim Putra dan aing nyebutna kan Hakim gini. Aing mah Putra nyebutna si Putra gitu ya. Putra ge nya. Aing tiga nggak salah baru gitu baru dah itu aing mah bisa dulu aing mendesain desain dulu gitu sana itu kejuan itu aing suara aing baru apa aing kak aing pesan kira-kira atau di Polri kan sana banget sulit lebih kita kan masih si ani tak boleh banget aing tu dengar dia aing tu fikir dulu oh ini pelajaran deh soalnya kita besok aing kan gitu sih dulu mau apa di luar gitu kan gitu lihatnya dengan jelasnya terus gaya sia saya terus kayak aing ya saya dulu cari sini dia sebenarnya susah kalau gitu benar aja kayak ada teh eta buset ngos-ngos karakter banting wah ya banting coba di sini deh benar lain pas itu aduh tuh Sekarang video buatan dirinya. Wih, yang terus siang mana banyak siang huruf ya. Bukan itu anjing. Susah susah juga sembilan kelas ini kayak berat. Aing kekuatan kayak istirahat itu juga gitu capek anjing bisa bisa. Nhìn kiểu nó lại hả. Baru mana anjing. bisa dibuat nah situs video titik harus gitu lah. Jumlah. Nah, ush. Ay, si buat kan cuma satu.
In this last section,
Ih, aya lem deui wae eta. Aya.
In this last section, we'll learn about BigQuery, which is Google's fully managed, petabyte-scale, low-cost analytics data warehouse. BigQuery is a fully managed, serverless data warehouse. A data warehouse is a large store that contains terabytes and petabytes of data gathered from a wide range of sources within an organization, and it's used to guide management decisions. Being fully managed means that BigQuery takes care of all the underlying infrastructure, so you can focus on using SQL queries to answer business questions without worrying about deployment, scalability, and security. Let's look at some key features of BigQuery. 1. BigQuery provides two services in one: storage plus analytics. It's a place to store petabytes of data. For reference, 1 petabyte is equivalent to 11,000 movies at 4K quality. BigQuery is also a place to analyze data with built-in features like machine learning, geospatial analysis, and business intelligence, which we'll explore a bit later on. 2. BigQuery is a fully managed serverless solution, which means that you use SQL queries to answer your organization's biggest questions in the front end without worrying about infrastructure in the back end. If you've never written SQL before, don't worry. This course provides resources and labs to help. 3. BigQuery has a flexible pay-as-you-go pricing model, where you pay for the number of bytes of data your query processes and for any permanent table storage. If you prefer to have a fixed bill each month, you can also subscribe to flat rate pricing, where you can have a reserved amount of resources for use. 4. Data in BigQuery is encrypted at rest by default without any action required from a customer. By encrypted at rest, we mean that encryption is used to protect data that is stored on a disk, including solid-state drives or backup media. And 5, BigQuery has built-in machine learning features, so you can write ML models directly in BigQuery by using SQL. Also, if you use other professional tools, such as Vertex AI from Google Cloud, to train your ML models, you can export datasets from BigQuery directly into Vertex AI for a seamless integration across the data to AI lifecycle. So what does the typical architecture of a data warehouse solution look like? The input data can be either real-time or batch data. If it's streaming data, which can be either structured or unstructured, high speed and large volume, PubSub is needed to digest the data. If it's batch data, it can be directly uploaded to cloud storage. After that, both pipelines lead to data flow to process the data. Data flow is where we extract, transform, and load the data if needed. BigQuery sits in the middle to link data processes by using data flow and data access through analytics, AI, and ML tools. The job of the analytics engine of BigQuery at the end of a data pipeline is to ingest all the processed data after ETL, store and analyze it, and then possibly output it for further use, such as data visualization and machine learning. BigQuery outputs usually feed into 2 buckets: business intelligence tools and AI and ML tools. If you're a business analyst or data analyst, you can connect to visualization tools like Looker, Looker Studio, Tableau, or other BI tools. If you prefer to work in spreadsheets, you can query both small or large BigQuery datasets directly from Google Sheets and even perform common operations like pivot tables. Alternatively, if you're a data scientist or machine learning engineer, you can directly call the data from BigQuery using Vertex AI AutoML Tabular for automated modeling, or pull it into Vertex AI Workbench for custom development. These AI and ML tools are part of Vertex AI, Google's unified ML platform. BigQuery is like a common staging area for data analytics workloads. When your data is there, business analysts, BI developers, data scientists, and machine learning engineers can be granted access to your data for their own insights. BigQuery can ingest datasets from various sources, including internal data, which is data saved directly in BigQuery, external data. BigQuery also offers the option to query external data sources, like data stored in other Google Cloud storage services, such as Cloud Storage, or in other Google Cloud database services, such as Spanner or Cloud SQL, and bypass BigQuery managed storage. This means that a raw CSV file in cloud storage or a Google Sheet can be used to write a query without being ingested by BigQuery first. Multi-cloud data, which is data stored in multiple cloud services such as AWS or Azure, and public datasets. If you don't have data of your own, you can analyze any of the public datasets available in the cloud marketplace. After the data is stored in BigQuery, it's fully managed and is automatically replicated, backed up, and set up to autoscale. You can use 3 basic patterns to load data into BigQuery. The first is a batch load, where source data is loaded into a BigQuery table in a single batch operation. This can be a one-time operation, or it can be automated to occur on a schedule. A batch load operation can create a new table or append data into an existing table. The second is streaming, where smaller batches of data are streamed continuously so that the data is available for querying in near real time. And the third is generated data, where SQL statements are used to insert rows into an existing table or to write the results of a query to a table. Of course, the purpose of BigQuery is not to just store data. It's for analyzing data and helping to make business decisions. BigQuery is optimized for running analytic queries over large datasets. It can perform queries on terabytes of data in seconds and petabytes in minutes. This performance lets you analyze large datasets efficiently and get insights in near real time. Looker, Looker Studio, and many integrated partner tools can be used to draw analytics from BigQuery and build sophisticated interactive data visualizations. BigQuery also has built-in capabilities for building machine learning models. An ML model lets you solve certain kinds of problems at scale by using data examples, but without the need for custom code. Machine learning on large datasets requires extensive programming and knowledge of ML frameworks. These requirements restrict solution development to a small set of people within each company, and they exclude data analysts who understand the data but have limited machine learning knowledge and programming expertise. BigQuery ML empowers data analysts to use machine learning through existing SQL tools and skills. Analysts can use BigQuery ML to build and evaluate ML models in BigQuery. Analysts no longer need to export small amounts of data to spreadsheets or other applications, and they no longer need to wait for limited resources from a data science team. BigQuery ML functionality is available by using the BigQuery Web UI, the BQ command line tool, the BigQuery REST API, and an external tool such as Jupyter Notebook or Business Intelligence Platform. In this next lab, you'll use data prep to manipulate a dataset. You'll use data prep to import a dataset and In this next lab, you'll use data prep to manipulate a dataset. You'll use data prep to import a dataset and create recipes to interpret the data into meaningful results.
Nice. sampai di sertifikat deh, sampai di tingkat kepolisian. Hah? Lah, bentar, bentar. Bitcoin, mana Bitcoin, Cok? Oh ini anjing dari capek juga ya gua anjing 3. Ya Allah, ai capek amat sih ieu. Oh ini. Sampai kita mau lihat lagi baru udah. Kalau kuis, kalau video kita gasin aja gitu. Analisis, analisis. Iya, iya, enggak tadi, aing mah monyet. Nah, aing oge sih, aing. Dia cuman banyak, banyak itu anjir. Itu cuma satu, cok. kamu minggu ini saya ya Allah ya aku bisa ini. Eh, bro. Hah. Gila bro, sampai 8 loh anjing. Nice, nice, nice.
This brings us to the end of the 9th module of the Google Cloud. This brings us to the end of the 9th module of the Google Cloud Computing Foundations course. Let's do a quick summary. First, you explored big data managed services in the cloud. Next, you examined using Dataproc to run Hadoop, Spark, and other big data technologies as a managed service in the cloud. Then you learned about building ETL pipelines as a managed service by using Dataflow. And finally, you explored BigQuery, which is a managed data warehouse and analytics engine.
Welcome to the final module of the Google Cloud Computing Foundations course. Welcome to the final module of the Google Cloud Computing Foundations course, Let Machines Do the Work. In this section of the course, you'll explore the world of machine learning and the role of machine learning in putting your data to work. This means that you'll define machine learning, ML, understand the terminology used and identify the value proposition, explore Vertex AI, Google's unified AI platform, and use Google APIs to apply a range of pre-trained ML models. The module agenda follows the objectives. It begins with an introduction to what machine learning is and how it works. Next, you'll explore the complexities behind developing ML models, but also how Vertex AI, Google's unified AI platform, makes it easier to take ML projects from ideation to production and deployment. Then, you'll learn how AutoML can be used to train high-quality, custom machine learning models with minimal effort or machine learning expertise. Next, you'll see how custom training allows you to have the control over the entire ML development process. From there, you'll explore different pre-trained ML APIs that Google has made available for common applications. After that, you'll complete 3 hands-on labs on the Cloud Natural Language API, the Speech-to-Text API, and on video intelligence. Finally, the module concludes with a short quiz and a recap of the topics covered. Let's get started. The world is filled with things that most of us can understand and react to without much thought. For example, a stop sign partially covered by snow is still a stop sign, and a chair that's 5 times bigger than usual is still a place to sit. But for computers, which don't have the benefit of growing up and learning the nuances of these objects, the world is often messy and complicated. In this first section, you'll start by watching a video called Making Sense of a Messy World, where Google engineers and researchers discuss how machine learning is improving computers and many of the things we use them for, such as maps, search, recommending videos, and translations. Let's watch this short video now.
You ready to start right now?
Yeah, thank you.
There have been a number of shifts in the way we think about computing over the past few decades.
The terminology artificial intelligence has come in and out of favor in the scientific community. Sometimes it's called machine learning.
We tend to call it machine intelligence these days.
I just call it intelligence.
And sometimes it's just the effort to build machines that are better.
So in the early days, everything was built on logic, doing mathematical integration problems, playing chess. But we realized that what the real challenges were the things that people can do every day.
The real world is actually very messy. Hard logical rules are not the way to solve really interesting real-world problems.
You have to have a system that'll learn to get the knowledge in. You can't just program it all in.
Artificial intelligence is an effort to build machines that can learn from their environment, from mistakes, and from people.
And we're still at the stage where we don't know what is the right path and the right breakthrough.
So, I mean, there's certainly a whole raft of different approaches.
One of the subfields we call pattern recognition.
Artificial neural network,
Reinforcement learning, for example.
statistical inference, and probabilistic machine learning.
Supervised learning, unsupervised learning, and we're not quite sure what technique is going to lead to better systems. And in fact, it's probably not one technique for everything. It's probably a bunch of different techniques and combinations of those techniques.
Any progress we make in building truly intelligent systems is going to depend on progress in technology generally.
And until recently, we didn't have computers that were fast enough or data sets that were big enough to do that.
And so being able to take a particular problem and spread it out over lots and lots of machines is a very important approach because it makes our research faster.
So there's applications of artificial intelligence around us all the time.
When it begins to work, or it does work, it's all of a sudden given another name.
We're all already using it and very comfortable with it.
Things that now we regard as routine, 30 years ago would have been regarded as amazing examples of artificial intelligence.
Anti-lock braking,
Autopilot systems for planes,
Search.
recommendations.
maps,
To decide whether or not this particular email is spam or not spam.
The ability to translate one language to another with your phone. 10 years ago, if you tried to talk to your computer or to your phone, that would just be hopeless.
We are seeing a steady torrent of these tricks, one after the other, getting figured out right now. And I think a lot of people that are close to the field have this, do have that kind of breathless sense that things are moving quickly.
It's a progressive thing. It's about building things that are slightly better, slightly better, slightly better.
Intelligence is really not going to be something that we ever succeed in defining in a succinct and singular way. It's really this whole constellation of different capabilities that all kind of are beautifully orchestrated and working together.
Predicting the long-term future is very difficult. Nobody can really do it. And the bad thing to do is take whatever's working best now and assume the future is going to be like that forever.
In that video, you heard a few different definitions of artificial intelligence and machine learning. Let's explore the differences together. Artificial intelligence, or AI, is an umbrella term that includes anything related to computers mimicking human intelligence. For example, in an online word processor, robots perform human actions for spelling and grammar checks. Machine learning is a toolset, like Newton's laws of mechanics. Just as you can use Newton's laws to learn how long it will take a ball to fall to the ground if you drop it off a cliff, you can use machine learning to solve certain kinds of problems at scale by using data examples, but without the need for custom code. You might have also heard the term deep learning or deep neural networks. Deep learning is a subset of machine learning that adds layers in between input data and output results to make a machine learn at more depth. It's a type of machine learning that works even when the data is unstructured, like images, speech, video, natural language text, and so on. Image classification is a type of deep learning. A machine can learn how to classify images into categories when it's shown lots of examples. The basic difference between machine learning and other techniques in AI is that in machine learning, machines learn. They don't start out intelligent, they become intelligent. So, how do machines become intelligent? Intelligence requires training. To train a machine learning model, examples are required. For example, to train a model to estimate how much you'll owe in taxes, you must show the model many examples of tax returns. Or if you want to train a model to estimate trip time between one location and another, you'll need to show it many examples of previous journeys. The first stage of ML is to train an ML model with examples. An example consists of an input and the correct answer for that input. This is called the label. In the case of structured data, that's rows and columns, an input can simply be a single row of data. In unstructured data, like images, an input could be a single image of a cloud that you want to classify as a rain cloud or not. Imagine you work for a manufacturing company and you want to train a machine learning model to detect defects in the parts before they're assembled into products. You'd start by creating a dataset of images of parts. Some of those images would be good and some parts would be defective. For each image, you'll assign a corresponding label and use that set of examples to train the model. An important detail to emphasize is that a machine learning model is only as good as the data used to train it. And a good model requires a lot of training data of historical examples of rejected parts and parts in good condition. With these elements, you can train a model to categorize parts as defective or not. The basic reason why ML models need high-quality data is because they don't have human general knowledge. Data is the only thing they have access to. After the model has been trained, it can be used to make predictions on data it's never seen before. In this example, the input for the trained model is an image of a part. Because the model has been trained on specific examples of good and defective parts, it can correctly predict that this part is in good condition. Algorithms, or ML models, are standard. That means that they exist independently of the use case. Although detecting manufacturing defects in images and detecting disease leaves in images are two different use cases, the same algorithm, which is an image classification network, works for both. Similarly, standard algorithms predict the future value of a time series, or to transcribe human speech to text. ResNet, for example, is a standard algorithm for image classification. It's not essential to understand how an image classification algorithm works, only that it's the algorithm we should use if we want to classify images of automotive parts. When we use the same algorithm on different datasets, different features or inputs are relevant to the different use cases, and we can see them represented visually here. You might be wondering, isn't the logic different? You can't possibly use the same rules to identify defects in manufacturing that you use to identify leaves. The logic is different, but machine learning doesn't use logical rules. The image classification network isn't a set of basic if this then that rules, but rather a function that learns how to differentiate between categories of images. So, although you start with the same standard algorithm, after training, the trained model that classifies leaves is different from the trained model that classifies parts. And you can actually reuse the same code for other use cases that are focused on the same kind of task. In our example, you identified manufacturing defects, but the higher level task classified images. This means you can reuse the same code for another image classification problem, like finding examples of products in photos posted on social media. However, you still have to train it separately for each use case. Much of the excitement around ML is because the barriers to entry have fallen. You don't need to be an astrophysicist to do machine learning. This is because of the convergence of several factors: the increasing availability of data, the increasing maturity and sophistication of ML algorithms, and the increasing power and availability of computing hardware and software. Google Cloud offers 4 options for building machine learning models. The first option is BigQuery ML. You'll remember from the previous module of this course that BigQuery ML is a tool for using SQL queries to create and execute machine learning models in BigQuery. If you already have your data in BigQuery and your problems fit the predefined ML models, this could be your best choice. The second option is AutoML, which is a no-code solution, so you can build your own machine learning models on Vertex AI through a point-and-click interface. The third option is custom training, through which you can code your own machine learning environment, the training, and the deployment, which provides you with flexibility and control over the ML pipeline. And finally, there are pre-built APIs, which are application programming interfaces. This option lets you use machine learning models that have already been built and trained by Google, so you don't have to build your own machine learning models if you don't have enough training data or sufficient machine learning expertise in-house. Let's play a quick game where we'll see how a neural network can learn how to recognize doodling. During the process, we'll help to teach it by adding our drawings to the world's largest doodling dataset and help with machine learning research. Pause the video now, and in a different browser tab or window, head to quickdraw.withgoogle.com. When you're done, head back here to continue the video. Here's the model behind the game we just played. It's called a deep neural network, or DNN. The layers are meant to mimic our own human brains in the way we perceive stimuli. With each layer, the model learns more about the image of this dog that's hiding in a laundry basket, starting from basic edges and colors, to a final decision of cat or dog. You'll build your own image recognition model later in the course. Spoiler alert, you don't need to write any code. But if you want additional information about how these model types work, see the TensorFlow Neural Network Playground. The TensorFlow Neural Network Playground at playground.tensorflow.org is a great interactive learning tool for understanding how computers think and shows how far ML has come that we can build these models at scale like in Google Photos. Now that you've got a better understanding of what machine learning is, let's explore what it takes to build a machine learning model. Now that you've got a better understanding of what machine learning is, let's explore what it takes to build a machine learning model and how Vertex AI can make that process easier for ML developers, data scientists, and data engineers. For years now, Google has invested time and resources into developing big data and AI. Google has developed key technologies and products, from its roots in the development of scikit-learn back in 2007 to Vertex AI today. As an AI-first company, Google has applied AI technologies to many of its products and services, like Gmail, Google Maps, Google Photos, and Google Translate. But developing these technologies doesn't come without challenges, especially when it involves developing machine learning models and putting them into production. Some traditional challenges include determining how to handle large quantities of data, determining the right machine learning model to train the data, and harnessing the required amount of computing power. Then there are challenges around getting ML models into production. Production challenges require scalability, monitoring, and continuous integration and continuous delivery or deployment. In fact, according to the technological research and consulting firm Gartner, only half of enterprise ML projects get past the pilot phase. And finally, there are ease-of-use challenges. Many tools in the market require advanced coding skills, which can take a data scientist's focus away from model configuration. And without a unified workflow, data scientists often have difficulties finding tools. Google's solution to many of the production and ease-of-use challenges is Vertex AI, a unified platform that brings all the components of the machine learning ecosystem and workflow together. So what exactly does a unified platform mean? In the case of Vertex AI, it means having one digital experience to create, manage, and deploy models over time and at scale. For example, during the data readiness stage, users can upload data from wherever it's stored, cloud storage, BigQuery, or a local machine. Then, during the feature readiness stage, users can create features, which are the processed data that will be put into the model, and then share them with others by using the feature store. After that, it's time for training and hyperparameter tuning. This means that when the data is ready, users can experiment with different models and adjust hyperparameters. And finally, during deployment and model monitoring, users can set up the pipeline to transform the model into production by automatically monitoring and performing continuous improvements. And to refer back to the different options that we explored earlier, Vertex AI allows users to build machine learning models with either AutoML, a no-code solution, or custom training, a code-based solution. AutoML is easy to use and lets data scientists spend more time turning business problems into ML solutions, while custom training enables data scientists to have full control over the development environment and process. Being able to perform such a wide range of tasks in one unified platform has many benefits. This can be summarized with 4 S's. It's seamless. Vertex AI provides a smooth user experience from uploading and preparing data all the way to model training and production. It's scalable. The machine learning operations, MLOps, provided by Vertex AI helps to monitor and manage the ML production, and therefore scale the storage and computing power automatically. It's sustainable. All of the artifacts and features created with Vertex AI can be reused and shared. And it's speedy. Vertex AI produces models that have 80% fewer lines of code than competitors. Now let's shift our focus to one of the machine learning options mentioned earlier, AutoML. AutoML is a no Now let's shift our focus to one of the machine learning options mentioned earlier, AutoML. AutoML is a no-code solution to build ML models through Vertex AI. It allows users to train high-quality custom machine learning models with minimal effort or machine learning expertise. To understand AutoML, which is short for automated machine learning, let's briefly look at how it was built. If you've worked with ML models before, you know that training and deploying ML models can be incredibly time-consuming because you need to repeatedly add new data and features, try different models, and tune parameters to achieve the best result. To solve this problem, when AutoML was first announced in January of 2018, the goal was to automate machine learning pipelines to save data scientists from manual work, such as tuning hyperparameters and comparing against multiple models. But how could this be done? Well, machine learning is similar to human learning. It all starts with gathering the right information. For AutoML, two technologies are critical. The first is known as transfer learning. With transfer learning, you build a knowledge base in the field. You can think of this like gathering many books to create a library. Transfer learning is a powerful technique that lets people with smaller datasets or less computational power achieve state-of-the-art results by using pre-trained models that have been trained on similar, larger datasets. Because the model learns through transfer learning, it doesn't have to learn from the beginning, so it can generally reach higher accuracy with much less data and computation time than models that don't use transfer learning. The second technology is neural architect search. The goal of neural architect search is to find the optimal model for the relevant project. Think of this like finding the best book in the library to help you learn what you need to. AutoML is powered by the latest machine learning research, so although a model performs training, the AutoML platform actually trains and evaluates multiple models and compares them to each other. This neural architecture search produces an ensemble of ML models and chooses the best one. Using these technologies has produced a tool that can significantly benefit data scientists. One of the biggest benefits is that it's a no-code solution. That means it can train high-quality custom machine learning models with minimal effort and requires little machine learning expertise. This allows data scientists to focus their time on tasks like defining business problems or evaluating and improving model results. Others might find AutoML useful to quickly prototype models and explore new datasets before investing in development. This might involve using it to identify the best features in a dataset, for example. So how does AutoML work exactly? AutoML supports 4 types of data: image, tabular, text, and video. For each data type, AutoML solves different types of problems called objectives. To get started, upload your data into AutoML. It can come from cloud storage, BigQuery, or even your local machine. From there, inform AutoML of the problems you want to solve. Some problems might sound similar to those mentioned in pre-built APIs. However, the major difference is that pre-built APIs use pre-built machine learning models, but AutoML uses custom-built models. In AutoML, you use your own data to train the machine learning model and then apply the trained model to predict your goal. But in pre-built APIs, the models are already trained with Google's datasets. You use the training results to predict your data. In reality, you may not be restricted to just one data type and one objective, but rather need to combine different objectives to solve a business problem. AutoML is a powerful tool that can help across these different data types and objectives. Now let's explore custom training. Custom training Now let's explore custom training. Custom training lets you code your own ML environment to control the entire ML development process, starting from data preparation to model deployment. If you want to code your machine learning model, You can use this option by building a custom training solution with Vertex AI Workbench. Workbench is a single development environment for the entire data science workflow, from exploring to training and then deploying a machine learning model with code. Before any coding begins, you must determine what environment you want your ML training code to use. There are two options, a pre-built container or a custom container. Imagine that a container is a kitchen. A pre-built container would represent a fully furnished room with cabinets and appliances, which represent the dependencies, that includes all the cookware, which represents the libraries, you need to make a meal. So if your ML training needs a platform like TensorFlow, PyTorch, Scikit-learn or XGBoost, and Python code to work with the platform, a pre-built container is probably your best solution. A custom container, alternatively, is like an empty room with no cabinets, appliances or cookware. You define the exact tools that you need to complete the job. When using AutoML, you define a domain-specific, labeled training dataset that's used to create the custom ML model you require. However, if you don't need a domain-specific dataset, Google's suite of pre-built ML APIs might meet your needs. In this section, you'll explore some of those APIs. Good machine learning models require lots of high-quality training data. You should aim for hundreds of thousands of records to train a custom model. If you don't have that kind of data, pre-built APIs are a great place to start. Pre-built APIs are offered as services. Often they can act as building blocks to create the application you want without the expense or complexity of creating your own models. They save the time and effort of building, curating, and training a new dataset so you can directly deal with predictions. So, what are some of the pre-built APIs? Let's explore a short list. The Speech-to-Text API converts audio to text for data processing. The Cloud Natural Language API recognizes parts of speech called entities and sentiment. The Cloud Translation API converts text from one language to another. The Text-to-Speech API converts text into high-quality voice audio. The Vision API works with and recognizes content in static images. And the Video Intelligence API recognizes motion and action in video. And Google has already done a lot of work to train these models by using Google datasets. For example, the Vision API is based on Google's image datasets. The Speech-to-Text API is trained on YouTube captions. And the Translation API is built on Google Translate. You'll recall that how well a model is trained depends on how much data is available to train it. As you might expect, Google has many images, text, and ML researchers to train its pre-built models. This means less work for you. Let's take a minute and explore the Vision API in a browser. Start by navigating in a new Chrome tab or window to cloud.google.com/vision. Then you can scroll down and try the API by uploading an image. You can actually experiment with each of the ML APIs in a browser. When you're ready to build a production model, you'll need to pass a JSON object request to the API and parse what it returns. Here's a real example of how Bloomberg, a US-based financial, software, data, and media company, benefits from the Cloud Translation API.
In financial markets, getting information quickly is the name of the game, and our 5,000 engineers work on the systems that do this at scale. You'll typically see a headline from a news event come out, and sometimes seconds later, the entire market move can be over.
Bloomberg is a truly global company. Not only are our clients all over the world, but our employees are also all over the world.
More and more news and information that was critical for financial markets was breaking in local language in other countries.
Within our news product, we aggregate news from hundreds of thousands of different sources, and making that information available, accessible to our customers at a moment's notice in a language that they understand and that they can interpret was really critical for us.
Translation and automated translation could make that information accessible to a much broader universe. We deal and operate in 40 languages, more than 170 countries. We needed something that was much better and much wider and broader. So in contracting with Google and approaching them, we said, what is your product? What can translation do for us? And in this case, it was an existing product. It had easy connectivity. So our engineers were able to integrate it into our platform seamlessly.
We were able to actually see translation happening in real time. So it was a pretty seamless, pretty easy process. It's extremely important for our customers to be able to access information wherever they are. We decided that we wanted to add the ability for people across the world to see that news translated in the language that was most useful to them. We wanted to add the ability for people across the world to access hundreds of thousands of news stories a day in the language that was most useful to them. It just worked almost like magic.
Going to see customers and see them using the product is really exciting. They're just like, that is fantastic.
busuk siap stop وعلى
It's time for hands-on practice with some of the pre-built APIs. It's time for hands-on practice with some of the pre-built APIs. In the 3 final labs of this course, you'll explore a few of the pre-trained machine learning APIs, starting with the Cloud Natural Language API. In the lab titled Cloud Natural Language API Quick Start, you'll apply the Analyze Entities method to ask the Cloud Natural Language API to extract entities, for example people, places, and events, from a snippet of text. During this lab, you'll create an API key and make an entity analysis request. Next, you'll find the speech-to-text API. In the lab titled Speech-to-Text API Quick Start, you'll use a pre-recorded file to create and call a speech-to-text API request. During this lab, you'll create an API key, create a speech API request, and call the speech API request.
Okay, I try to do. Hah? Anjir. nice. Yo, kayak rusak di kabel wah, rusak jiwa. Jadi,
Let's finish this module with the video. Let's finish this module with the Video Intelligence API. In the lab titled Video Intelligence Quick Start, you'll make an annotated video request by using the Video Intelligence API. During this lab, you'll enable the Video Intelligence API, set up authorization, and make an annotated video request.
mesti gampang sih. Biasa aja, Cok. Ya emang harus boleh sih. Edukasi. Oh gitu. Itu. Anjing. Hah? Nah, nice bisa lagi bro.
This brings us to the end of the 10th and final module of the Google Cloud. This brings us to the end of the 10th and final module of the Google Cloud Computing Foundations course. Let's do a quick summary. You started by exploring machine learning. You defined machine learning as a term, explored the terminology used, and identified the value proposition. After that, you explored Vertex AI, Google's unified AI platform. You saw the options available to you with AutoML, Google's no-code solution to build ML models, and also custom training, which lets you code your own ML environment to have the control over the entire ML development process, starting from data preparation to model deployment. And finally, you learned about Google APIs to apply a range of pre-trained ML models.
Thank you, bro.
Congratulations on completing the Google Cloud Computing Foundations course. Congratulations on completing the Google Cloud Computing Foundations course. The goal of this course was to provide an overview of and hands-on practice with the concepts related to cloud basics, big data, and machine learning, and help you understand where and how Google Cloud fits into this environment. Let's quickly review the modules we covered in the course. In Module 1, you began by exploring what the cloud is and why it's a technological and business game changer. In Module 2, you examined the different ways a user can interact with Google Cloud. Module 3 introduced how to use Google Cloud resources and serverless managed services to build applications, followed by Module 4 that addressed how to implement various structured and unstructured storage models. In Module 5, you learned about different application managed service options that exist in the cloud. And then in Module 6, you learned how security is administered in Google Cloud. In Module 7, you explored how secure networks are built in the cloud. And in Module 8, you identified the different tools that support cloud automation and management. In Module 9, you examined various managed big data services in the cloud. And in Module 10, the course ended with an introduction to machine learning, some terminology used, and its value proposition. You can demonstrate your knowledge of the concepts covered in this course by completing a knowledge-based assessment. Also, you have the opportunity to demonstrate your skills and earn 4 digital Google Cloud skill badges. The basics of Google Cloud Compute, set up an app dev environment on Google Cloud, build a secure Google Cloud network, and prepare data for ML APIs on Google Cloud. Fortunately, you've already made great progress with each skill badge by completing the hands-on labs during the course. However, these labs were only stepping stones to prepare for the final challenge lab of each skill badge. The first step to completing the skill badges is to ensure that you've enrolled for each one. The skill badge outline will list all of the labs to be completed. You should have completed the hands-on labs during the course, but if you haven't, please complete these first. The final lab in the skill badge outline is the challenge lab, which will test your skills and knowledge from the other labs in the skill badge. After you've completed the challenge lab, and if all the other labs are complete, you'll be awarded a skill badge. Feel free to share this achievement on social media and be sure to add it to your resume. After you've completed the knowledge assessment and earned your Google Cloud skill badges, you should be in a position to access the enterprise-level Google Cloud content that's available on Google Skills to continue your development. If this is part of your plans, you should also be well-placed to enroll into career readiness programs to prepare for Associate Cloud Engineer certifications. Good luck!
you.